Dear students, continuing with our lecture series on oxidation reactions, this is our second lecture on oxidation reactions, and in this lecture we will discuss about manganese compounds as oxidizing agents. Manganese, which is having an atomic number of 25, is the 12th most abundant element on Earth's crust. And the most common oxidation states in which these manganese compounds they can act as either oxidizing agents or they help in oxidation is plus 2 plus 3 plus 4 plus 6 and plus 7. Whereas the plus 2 oxidation state which has a pale pink color due to spin forbidden DD transition. This is found in living organism for essential functions. Whereas oxidation plus 7 is a deep purple in color and it acts as a strong oxidizing agent where the manganese 7 is reduced to manganese 2 plus by using 5 electrons. And most common example is potassium permanganate in this case. And out of different types of these manganese compounds, these three oxidation states, they are very important, which act as oxidizing agent. Manganese 3 reagents, manganese 4 reagents, and manganese 7 reagents. So all these three, they act as strong oxidizing agents, which can be used in organic chemistry for different types of functional group transformations. So first is use of manganese 3 oxidants. Manganese 3 oxidants and most commonly used manganese 3 oxidant is manganese acetate. So manganese acetate basically is used for selective oxidation of benzylic and allylic alcohols. So you can see this is an example of allylic alcohol. So when this allylic alcohol, cinnamyl alcohol, is reacted with manganese acetate, then this primary alcoholic group is oxidized to an aldehydic functional. So we will get alpha beta unsaturated ketones as the product. Cinnamaldehyde is formed as the product from oxidation of cinnamyl alcohol. Similarly, this benzylic alcohol is oxidized to the ketone with use of manganese 3 acetate. And in addition to manganese 3 acetate, this DDQ 2,3 5 6 dicyano 1,4-benzoquinone is also used as co-oxidant for these types of reactions. Then sulfides, they can be oxidized to sulfones if we use these types of manganese catalysts, which is formed from different types of Schiff bases complex. This is a alpha hydroxy Schiff base, and dimer of this is used in making a complex with manganese 3, and this perchlorate salt of manganese is used as a catalyst which oxidizes the sulfide group into sulfone. Similarly, the manganese 3 oxidants, they are also used for asymmetric of oxidation of alkenes, which is very important in case of pharmaceutical chemistry. So two catalysts which have shown promise in recent years is Jacobson's catalyst, which is this catalyst, and Katuski catalyst, which is this catalyst. Only difference is this aromatic ring substitution in these, and in addition here this chlorine group is introduced on reaction of the saline with NaOCl, which will give us the Jacobson catalyst. So here, when alkenes they are reacted with these catalysts in presence of NaOCl, then these stereochemical uh, epoxides they are formed. So asymmetric epoxides they are formed as the product in both the cases. And here the co-oxidant used is NaOCl, whereas here ido oxide is phenyl idoxide is used as the co-oxidant. Some applications of this Jacobson or Kotuski asymmetric of oxidation is in case of azulene. This gives us this type of stereochemical epoxide as the product, which can undergo reaction with acetonitrile to give us this type of oxazole, and this oxazole on hydrolysis gave us stereochemically important amino alcohols as the product, which are used as substrates for synthesis of different drug molecules. Similarly, these types of alkenes they undergo oxidation to give us these types of enantiomeric epoxides, and these on reaction with the two piridones they give us these types of drug molecules which act as potassium channel activators for hypertension. Then the mechanism for these types of reactions, that there may be three types of different mechanism, but before that the Jacobson catalyst, as I have told you, that is used in combination with another co-oxidant NaOCl. So when this saline manganese 3 saline is reacted with NaOCl, then this is oxidized to manganese 4 saline. This manganese will have the double bonded oxygen to it, and this will act as an active catalyst for transformation of different alkenes to the epoxide. So this is abbreviated like this. So in the mechanism we will use this active catalyst for different type of mechanism which can be possible for different type of alkenes. So this active catalyst when reacted with alkenes, they can have product formation through these different three types of mechanism. The mechanism can either be metallo-oxidation mechanism, or it can be a concerted mechanism, or it can be a radical mechanism. So in case of metallo-oxidation mechanism, this active catalyst interacts with the alkane to give us this type of four-membered intermediate, where addition of this manganese and oxygen to the alkene take place in cis manner, and then elimination of rest of the complex with manganese uh, in the inactive form. This one, that is manganese 3 saline, is reformed in this case, and this is converted into cis epoxide as the product. And then this inactive catalyst manganese 3 saline can again interact with NaOCl, and then it can be converted into an active catalyst. Then in case of concerted mechanism, this active catalyst reacts with the alkene to form this type of intermediate, where the alkene forms a transition bonds with this oxygen of the active catalyst, and this oxygen is transferred to the alkene in a cis manner to give us this type of cis product, and the active catalyst is converted into an inactive manganese 3 silane, and this manganese 3 silane can again be converted by NaOCl into the active. Then third type of mechanism is a radical mechanism, that here this interacts with this oxygen to form a transition bond, and a radical is formed over here. And then the removal of this oxygen from here to give us either a trans product or a cis product. A cis product is formed if this radical immediately collapses to give us, with the elimination of the inactive part of the molecule, to give us this cis product. But if there is sufficient time for this radical to rotate, then we can have a trans product also. Then is manganese 4 oxidants. They can also undergo oxidation of alcohols. So there are many examples of using MnO2, manganese dioxide, for these types of transformation. So for example, most common is conversion of retinol into retinate, or vitamin A into retinol. So you can see over here the this part is an allylic alcohol, and in presence of manganese dioxide, using pentane as solvent at room temperature, this primary hydroxyl group can be converted into an aldehydic functional group, and further oxidation to carboxylic acid does not take. So in this way, this manganese dioxide is a selective reagent for oxidation of primary alcohols to aldehydes. Similarly, in this case also, this is the primary alcohol functional group. This is a secondary alcohol functional. And manganese dioxide is very selective, that it oxidizes only primary alcoholic or primary hydroxyl functional group into an aldehyde. And you can see over here, even carbon-carbon double bonds and secondary hydroxyl group present in the molecule is not affected by this oxidizing agent. So in this way also, this is a very selective reagent for oxidation of only allylic alcohols, benzylic alcohols, or primary alcohols as the primary alcohols to their corresponding aldehydes. So this benzyl alcohol is oxidized to benzaldehyde by manganese dioxide under solvent-free conditions. Then aldehydes, they can be oxidized to esters using manganese 4 oxidants, and this oxidation is known as Corey-Gilman-Janum oxidation. So here, when benzaldehyde is reacted with manganese dioxide in presence of uh, sodium cyanide, methanol, and acetic acid, this is converted into the corresponding ester of the benzaldehyde. Similarly, in this case, if we use this aldehyde functional group, where we are having other functional group also present in the substrate like epoxides and secondary hydroxyl group, the manganese dioxide in presence of sodium cyanide and methanol and acetic acid will transform this aldehydic function group only to the ester function group. No other functional group like carbon-carbon double bond or epoxide ring or secondary hydroxyl group, they are affected. So in this way, this is also a very selective reagent for these types of transformations of aldehydes into esters. So basic mechanism of this reaction is the sodium cyanide and acetic acid which are used in the reaction, they first react with each other to generate HCN in situ, and that HCN reacts with the benzaldehyde, and we know that HCN adds to the carbon oxygen double bond to give us cyanohydrins as the product, and these cyanohydrins they undergo oxidation in presence of manganese acetate to give us alpha keto cyanides as the products, and these alpha keto cyanides are uh, they react with the methanol which is present, and this methanol act as a nucleophile which attacks the electrophilic carbon of the carbonyl group, which is attached to this electron withdrawing group, and this methoxy will get attached to this carbon of the carbonyl, and HCN is eliminated, CN from here and H from methanol, and we will get esters as the product. So this is how the aldehydes they are converted into esters in Corey-Gilman-Janum oxidation reactions. Then similarly, manganese dioxide can be used for the oxidation of carbon nitrogen compounds. For example, these secondary amines, they are oxidized to these types of carbon nitrogen double bonds. Shift bases, they are formed as the product. Similarly, these types of tertiary amines, when they are reacted with manganese dioxide in presence of chloroform, they can be converted into N-formyl amines as the product. So one of the methyl group is converted into aldehyde. Similarly, hydrazo compounds, nitrogen single bonds, they are converted into azobenzenes as the product when manganese dioxide is used as an oxidant. Then 1,2-diols, they can undergo oxidative cleavage to form dialdehydes as the products. So either aldehydes or ketones, they are formed as the product when diols they are reacted with manganese dioxide in dichloromethane to give us, for example, cyclododecanol 1,2-diol is converted into dodecanediol as the product. Then manganese dioxide is also used for aromatization and dehydrogenation reactions of alicyclic compounds. For example, this 1, 2, 3, 4, 5, 8, 9, 10 octahydroanthracene can be converted into anthracene when manganese dioxide is refluxed with benzene as the solvent. Similarly, nitriles they can be converted into amides by using manganese dioxide under reflux conditions. Then manganese 7 oxidants, and most common among the manganese 7 oxidant is potassium permanganate. And this potassium permanganate is a very strong oxidizing agent, and its reactivity will depend upon whether we use this reagent under acidic conditions or neutral conditions or basic conditions. So in case of acidic solution, which is more effective, the manganese 7 is reduced to manganese 2, whereas in basic conditions the manganese 7 is reduced to manganese 4, that is manganese dioxide is formed during the reactions. So this can be used for different types of functional group transformations. For example, this potassium permanganate in the alkaline form can be used for oxidation of the aromatic side chain. So this aromatic side chain can be oxidized to the corresponding carboxylic group. And only thing is because the alkaline KMnO4 is sufficiently insoluble in organic solvents, we need to use some phase transfer catalyst like what neoammonium salts in addition to the alkaline KM. Then similarly, the aromatic rings, they can also be oxidized if we use KMnO4 in the alkaline form. So these carbon-carbon double bonds of the aromatic ring, they are oxidized to the carboxylic group. So quinoline or isoquinolines, they can be oxidized to dicarboxylic acids in presence of alkaline potassium. Similarly, alcohols, they can be oxidized to carbonyl compounds, aldehydes or ketones when we use potassium permanganate in aqueous sodium dihydrogen phosphate. Then aldehydes, they can be oxidized to the corresponding carboxylic acids when KMnO4 is used as an oxidizing agent under acidic conditions. Similarly, in this case, this aldehydic form will be oxidized to carboxylic acid, and you can see that this is a selective oxidizing agent because here the ester group which is present in the molecule is not affected by the oxidizing agent. Then cycloalkenes, they can undergo 1,2 dihydroxylation reactions, and we will get cis-1,2-diols as the product. 1,2-cyclohexane-diol will be formed as the product. The mechanism of this reaction is that cyclohexene first react with KMnO4 and an intermediate cyclic ester of this type is formed. And this cyclic ester then undergo alkaline hydrolysis and we will get cis-diols as the product. Now one more reagent is Lumex von Rudolph reagent. Here KMnO4 in combination with the sodium periodate is used as the reagent for selective oxidation of the carbon-carbon double bond. So oxidative cleavage of this carbon-carbon double bond will take place and we will get carboxylic acids as the product. And this part will be oxidized to the ketone. These are the references which have been used for preparing this lecture. Thank you very much.